Hi guys, what's happening? We are going to talk about something called intermolecular forces. Okay? Intermolecular forces. Let's get it. Oh, I've got to share my screen. Silly me. Must share the screen. Okay, let's get us a piece of paper. Yeah, let's do this one today. And, oh yeah, those colors look good together. All right. Okay, guys. Intermolecular forces. And I am going to add some lines to this. All right, intermolecular forces, commonly referred to as IMS. These are the forces that hold, between molecules. Forces of attraction between molecules. They were commonly, they are also referred to as, oops, I almost forgot what I was doing. Van der Waal forces. Okay. Anyway, we don't need to write that. Don't worry about that. Okay, so just as an interstate connects states, an intermolecular force connects molecules. We have, oops, don't confuse this with intramolecular forces. These are within molecules. These are actually not forces, but chemical bonds. Okay? They are greater than, stronger than what we are talking about, which is not intra, but intermolecular. They are not within bonds. They are between, they are not within molecules. They are between molecules. And what we'll see is that solids have greater IMFs than do liquids, have greater IMFs than do gases. Okay? When you have a solid, as you know, the particles are neatly packed together and are only vibrating a little bit, right? The force that holds this molecule to this molecule is the intermolecular force, okay? For example, if we have HOH attached to another HOH, okay? Their attraction. This here is my molecule. This here is my molecule. This here is my attraction of one molecule to the other, right? We could put another oxygen here, right? Here's another molecule right here. And we could have him attracted. We could have forces of attraction between one molecule and the other molecule. Okay? These are intermolecular forces. It holds one piece of H2O to another piece. All right? I'm actually going to make this darker here. When you look at my H2Os that I just made darker, we could also identify that these are our intramolecular. Let me change that color. That's not a very good effective color. Those are our intramolecular forces. And in this case, they are covalent bonds. And they are stronger than our intermolecular forces, okay? When this solid has heat added to it, the molecules will gain kinetic energy. They will begin to move with more motion and energy, and they will slightly overcome these forces of attraction that are holding one molecule to another. So we'll see that the water molecules are now here, but they're a little bit further apart. And what that means is there are still attractive forces between one particle and another. However, they're not as strong. Thus, the liquid molecules can roll over one another. They don't spread apart. They're still attracted, but they can roll. That's why we can pour liquids. All right. Here we slightly overcame IMFs, right? If we continue to heat that liquid at some point, and we know that if it's liquid water, it will happen at right around 100 degrees Celsius, these molecules will have gained enough kinetic energy to completely overcome the intermolecular forces, right? Completely overcome IMFs. All right. So as we go from the solid to the liquid, we pull them apart. We kind of overcome those forces of attraction. As we go from the liquid to the gas, we totally overcome forces of attraction. And we actually assume that no intermolecular forces are present. That is a common assumption, such that the particles are as far apart as they can be. They're not drawn to each other. There are different types of intermolecular forces. There are different types of forces that hold molecules together. There are three. There are London dispersion forces. These are forces between all types of molecules, okay? And the only force between non-polar covalent molecules. All right, cool. Cool. We learned how to determine if something was polar or non-polar, didn't we? All right, so that's your first type of force. After that, we've got dipole forces. Okay, well, this is the type of force that exists between polar molecules. Okay? It is wherein you have a molecule. I don't want that to be my molecule. You have a molecule that has a partial positive and a partial negative end. And you have another molecule that has a partial positive and a partial negative end because they are polar. And it is the attractive force that exists between these two charged particles, which keep these molecules attracted to each other, because we know that positives attract negatives. So we see an attraction here, and that is essentially what holds this molecule in a sample of a solid or a liquid to this molecule. For our London dispersion forces, guys, we have a perfectly, right, we don't have any poles. So I could draw this as kind of like, that's my partial negative end, that's my partial positive end, right? Sorry, I'm just kind of redoing this. It's kind of a better way. This is my partial negative, partial positive. So right here, we have a force of attraction between the polar molecules. This is a much better drawing than the original one. Here, we do not have partial charges, but so the attraction here is not quite as strong, and I could get more into that later. However, what happens is one of these molecules will become temporarily polarized and cause the other molecule to also become temporarily polarized, and then we have this attraction there. And then our last type is something called hydrogen bonding. It is not a bond. It was originally thought to be a bond, but it is not. It is a force. It is a special type of dipole. All right. So it is a force of attraction between two dipoles, a partial positive and a partial negative. It occurs when H, hydrogen, is bonded to nitrogen, oxygen, or fluorine, such that when you have HF, we have a partial, very polar bond, negative, positive. Over here, we would have another HF, very polar bond, right? Positive, negative. And this positive and this negative form the, form the hydrogen bonding. Because hydrogen here is attached to fluorine, fluorine is very small and electronegative. Fluorine's charge is actually a little extra negative, causing him to be a little extra positive. Same thing happening over here. Due to the intensified positive and negative partial charges, we have a stronger force of attraction. Okay? The greater the magnitude of charge and the closer they can get, the stronger the attraction. All elements are very small. That allows them to get closer together and very partially charged. So we've got a greater charge. Think about, you've got two magnets. The closer you can get them together, the greater attracted they are, and the more charged they are. All right, so all of this increases the attraction. And this increased attraction only occurs when H himself is attached to a nitrogen, an oxygen, and a fluorine because of their small sizes, closer proximity, and extreme electronegativities, greater partial charge. So what we see is this is the, sorry, let me get a different color. This is the strongest of the intermolecular forces. This is the weakest of the intermolecular forces. And then this one is in the middle, okay? If you had something like H2, right? You go H, H, this is nonpolar, therefore it has London dispersion forces, okay? Very weak forces of attraction. We could look at something like HCl. It looks like this. Chlorine hogs the electrons, partial negative, partial positive. This is polar. Therefore, it has London dispersion forces because all solids and liquids experience London dispersion forces, but it also has dipole forces, okay? And then lastly, we could do H2O. Notice we have hydrogen attached to a small and extremely electronegative oxygen. So here we have London dispersion forces because they exist between all solids and liquids. We also have hydrogen bonding, which is the special type of dipole. If you see an OH group, that means you've got an O dash an H and that you have hydrogen bonding. Okay? All right, guys. Right on. I got it ends.